Okay. Second law of thermodynamics happened. We'll see some representative problems. Based on these problems, also you'll be in a position to understand the related theory. Or either way we can learn. Because since already you have come across this course and you have some idea of this course, of this thermodynamics. So no need to worry much about it. And as and when needed, we will also go through some relevant theory aspect. Okay, that is idea. ஏதாவது புரியலன்னா சொல்லுங்கம்மா. Hello.
Sir, okay, sir.
Okay.
புரியலன்னா சொல்லுங்க sir.
சரி, ரைட், ஃபைன். ஆடியோ இஸ் கிளியரா இருக்கா? நான் எனக்கு வேற செக் நான் வைக்கிறேன். ஆடியோ இஸ் கிளியரா?
Yes sir, clear sir.
Clear இல்லையா? சரி, ரைட்.
Yes sir, clear தான் sir.
Okay. From this point we'll start. Typical representative problems from second law of thermodynamics that we are going to see. Okay, I have taken these problem sheets here. The first one, very simple kind of problem, which is about finding the maximum work that can be obtained from heat engine. There is maximum. The cyclic engine exchanges heat with two reservoirs maintained at 100 and 300 degrees Celsius respectively. What is the maximum work that can be obtained from the extraction of 100 joule of heat from the hot reservoir? There is I will write this title: maximum work. Yeah, maximum work from a heat engine. So let us represent this schematically first. Yeah, schematic diagram we can make. Okay. So normally இந்த ஒரு நல்ல diagram போடுவோம் இல்லையா? And this is 1 minute. I will change the color here. So this is your TH and TC, and this is the work. This is QH and QC. So what are all given? TH, TC, and QH is given. Yeah. So this 1000 joule is extracted from a hot reservoir. Otherwise, QH is given as 1000 joule. And TH is given as 300 degrees Celsius. And TC at 100 degrees Celsius. So how to find the maximum work? So the maximum work is obtainable from a heat engine, what is called as a Carnot engine. Yeah. So we should write the formula for Carnot cycle. So what is the general definition for efficiency of a heat engine is simply W by QH. Fine, no? Which is work obtained for the amount of heat supply QH. From the amount of QH, how much is converted into work? So this is the formula of efficiency, which is going to give in fraction. And the maximum efficiency you can write, or this is this Q by WH. You can also write in terms of QH minus QC. This W is this W, no? This W is the difference of QH minus QC. From QH, some amount is converted to work, the rest is rejected to QC. So which is equal to QH minus QC by QH. And for the Carnot engine, you can replace this Q with temperature. So which is equal to TH minus TC by TH, or simply equal to 1 minus TC by TH. The formula fine. So what are all available now? Let us substitute. So okay, again to the maximum work. How do you find the maximum work? So So otherwise, if you take this eta max from this, you will be getting the efficiency maximum. Otherwise, you can also equate that to W maximum by QH. So we want to find this W maximum. Okay. So otherwise, this you can also equate to this one. Otherwise, this is the maximum efficiency for any heat engine. The maximum efficiency is given by Carnot formula. So this is the Carnot formula, and this is the general definition of efficiency. So this definition of efficiency in terms of work and heat, we are equating to the temperature values. Okay. Oh, yeah, one more person has joined. Okay. Thanks, Rohit, for joining. So we'll write this now. W maximum by QH equal to 1 minus TC by TH. So what are all available now? We except W max, everything is available. QH is 1000 equal to 1 minus TC by TH. So in this formula, this temperature is to be in Kelvin. Sometimes by mistake, if you are using this degree Celsius values, the result will be a different one. So please ensure that you are converting the temperature to Kelvin. So TC is 273 plus 100, so 373, and this is 273 plus 300, so 573. So what is the answer? Let's check any answer is matching. Yeah. From this right hand side, you'll be getting a efficiency. Multiply that with 1000, you'll be getting. I have a calculator from. Maybe calculation, you come arrive the answer now. Very simplest problem only you are looking in. 373 by 373 by 573.
0.35.
Tell me 3?
0.35.
Okay. There is a
35 into 1000 P2.
So this is 3.35. Yeah. Okay. So W maximum is you are getting into 350. Yeah.
Yes, sir.
So answer is 350 joule. Fine. Nice. Thanks. So the first option is correct. We can also check with already available solution. Maybe you can check that also. Okay. Will simply take that for granted. So this is correct answer. 349 is the nearest answer. Okay, my simplest problem only. Nothing difficult to understand this. Okay, so the word maximum is possible only for the Carnot engine. So we are using this Carnot engine formula. And another important thing to be kept in mind is this temperature are to be in Kelvin. If you do by mistake with degree Celsius, you'll be ending up with some other answer. Maybe this 651 you may be getting. So 300, what is it? 100 by 300, you'll be getting 1 minus. What is it? The other normally they will be giving these answer options in such a way that if you commit any mistake, you'll be ending up with other answer. That's a trick they are also having sometimes. Okay. Next one we shall go now. This problem is also quite the same. Heat engine operates at 75% of the maximum possible efficiency. Otherwise, this normal engine which is operating at 75% of the maximum possible efficiency. So the maximum possible efficiency you can get from the Carnot formula. That should be kept in mind. Okay, the other data are the ratio of heat source temperature in Kelvin. That is correct only. We are expecting the temperature in Kelvin. Here the heat source to heat sink is given as 5/3. So you are asked to find the fraction of heat supplied that is converted into work. So otherwise, what fraction of QH is converted into work? So fraction of heat is Q H by the fraction of heat supplied to which means simply W by QH. Correct, na? Fraction of heat supplied that is converted into work service, work divided by QH. That's what we are going to find. Service simply is what to say. It is nothing but the efficiency of your engine. At last, we are going to find the efficiency of the engine. So the efficiency of the engine is 75% of the maximum possible efficiency. So first, let us find the maximum possible efficiency. So let us give the title for this so that better to. So what is fraction of heat converted to work? So that is a title we can have, and let us represent the problem schematically. So I will take this. So wherever possible, always make the schematic so that your data will be very readily available. So what are all available? We have this heat. So efficiency equal to 0.75 of maximum efficiency. That's what is a given. And what is maximum efficiency? Maximum efficiency is given as the formula of 1 minus Tc by Th. And we are also given with the data of ratio of heat source, heat source temperature to heat sink temperature. Otherwise, Th by Tc is given. So otherwise, this is given in the reverse way. So we are given with that, which is equal to 1 minus just 3 by 5. Otherwise, we are given with Th by Tc, which is 5 by 3. Otherwise, Tc by Th is simply 3 by 5. So this is available. 1 minus 3. So this is equal to 2 by 5. Yeah. And maximum efficiency is 2 by 5. And efficiency is equal to 0.75 into 2 by 5. Correct, Amma? I suppose. So 2 by 5 raised is 0.4, 0.75 into 0.4. So which is equal to some 0.3. Yeah. Correct answer?
Yes, sir. 0.2.
Point. 0.3. So what is the meaning of this efficiency? This is actually giving W by QH. So what is asked is the fraction of heat supplied that is converted into work. The fraction of heat supplied, this is 0.3 is nothing but the fraction of heat supplied. The fraction of heat that is converted into work is simply this, W by H. Yeah, fraction of there is work obtained by heat supplied. This is what is the answer expected. Correct, Appa? Who is our Rohit? Are you listening, Pa? Maybe
sir, 0.3 da sir varudhu.
Seri, Pa. Right, thanks. Class, let us make it some interactive. Okay, I will mark it. Fine. Okay, ரெண்டு ப்ராப்ளம் பார்த்தாச்சு. எவ்வளவு நேரம் ஆயிடுச்சு? ஒரு 10-15 நிமிஷம். Okay, the similar one we are now going to extend. So till this part is fine. These are all with reference to the Carnot cycle formula. We'll go further. This is slightly altered one, but again still we are going to use the formula of Carnot. Nothing great here. Yeah, inventor claims to have developed a refrigeration unit. Sometimes this kind of evaluation problem, we can evaluate this process based on our Carnot analysis, Carnot cycle. Otherwise, we can simply compare the efficiency with Carnot cycle or compare the coefficient performance with Carnot refrigerator. That way, you can easily solve this kind of problem. They are given with the temperature levels and coefficient of performance. You can check this coefficient of performance with the maximum performance possible, and you can say about the claim whether this claim is feasible one or it's a false claim. So let me give the title here. Evaluating a claim. Let me change that. Evaluating a claim based on thermodynamics. So again, we are going to represent the schematic. This is process happening in the reverse direction. We are adding work from, we are taking a heat and rejecting to the surrounding at QH. So what is refrigerator space is at -3 degrees Celsius, and the high temperature, which is at 27 degrees Celsius. And COP, coefficient of performance, is defined as what is it? Amount of cooling produced. Say, what is it? Refrigeration for the refrigerator, it is QC by 1 minute. QC by it is useful output by input supply. Input is nothing but W. So QC by W is the formula. So otherwise W will be, you can write this W in terms of QH and QC. Otherwise, if you write this QH is equal to QC plus W. Otherwise, the heat rejected, this one, no? Which one? This QH is simply QC is also added, W is also added, which is going to leave out. So QH is equal to QC plus W. So from which you can write this W as QH minus QC, and we are going to use this here, which is QC by QH minus QC. The formula derive பண்றதுலாம் எப்பயும் கஷ்டப்பட தேவையில்லை. Always we are starting from the fundamentals. So always the coefficient of performance or efficiency or anything is useful output by the input supplied. In the case of refrigeration, useful output is nothing but the cooling produced. There is QC. QC is of importance. The refrigerator capacity or anything, we are worried only about how much cooling it is making. And input here is the work supply. Whereas in the previous cases, in the efficiency or efficiency definition, this work is a useful output, and input is the hot high temperature heat source, energy of the high temperature heat source. Okay, so always better to relate the content whatever we are discussing. That's why I'm going front and back. Okay, now we are writing this COP in terms of COP equal to QC by QH minus QC, and the maximum possible COP, which is equal to this entire Q you can write in terms of temperature. That is what is a COP of Carnot refrigerator. So for the Carnot refrigerator, we have TC by TH minus TC. Otherwise, wherever the formula is there in terms of temperature, which is normally based on the Carnot engine. Okay. Otherwise, in the case of the COP or efficiency, of course, we also sometimes do this COP calculation for the vapor compression cycle or any other cycle also. In that case, okay, you have to, the first ever formula we normally write is whenever we write this QC directly in terms of TC, this is for the Carnot cycle. Okay, now let us write what are all available to us, given to us. So again, this formula is applicable in terms of only in terms of Kelvin, yeah, COP max. So what is the COP max we are having? TC is -3 degrees Celsius. So -3 degrees Celsius are 270 Kelvin, yeah, 270 by, and 27 is 300, yeah, 300 minus 270. So always 270 by 30. So this is the COP 9. COP of 9 is the maximum possible, but the inventor is claiming a COP of his device to be 9.5. Otherwise, he's saying like he is having an engine or a refrigerator which is performing more than the ideal case. So ideal itself is only 9, whereas he is claiming to be 9.5. So definitely it's a false claim. Okay. So otherwise, we are simply saying the claim evaluation. This is simply based on the Carnot. The maximum engine, say maximum efficiency of the engine is given by Carnot. or maximum performance is given by Carnot refrigerator. So simply find the efficiency or COP simply from the Carnot formula. The Carnot formula is simply dealing with in terms of temperature. So you are asked to know the, or it is enough to know the lowest temperature and highest temperature. With that, we can find the COP or efficiency, and from that evaluation of COP or efficiency, we can simply say about the feasibility of any process. Yes, tell me, Pa.
சார் இப்ப நமக்கு ஒரு ஃபார்முலா இருக்குல்ல சார், அந்த COP of refrigerator is equal to 1 plus the efficiency of heat pump.
அதை ப்ரூவ் பண்ணணுமா?
இல்ல அது மூலமா கூட பண்ணலாம்ல சார். நம்ம இதுக்கு ஹீட் பம்போட எஃபிஷியன்சி, இது ஹீட் பம்பா வேலை செஞ்சா எவ்வளவு எஃபிஷியன்சி கொடுக்கும் பிளஸ்.
ஓகே, how do you find heat pump efficiency here?
முன்னாடி பண்ணமே சார்.
that is actually engine heat engine. ஆமா, heat engineங்கிறது வேற, heat pumpங்கிறது வேற. Heat pump, okay, for the heat pump normally we will write the COP as okay, இதுக்கு relevant I will also connect that. Say the heat pump means COP will write as QH by W. மாத்தி பண்ணுவீங்க. So heat pump is not simply heat engine. Heat pump means, say in the normally in the cold space, say always now the heat pump heat இதுக்கு என்ன difference சொல்லிறேன். அப்போ say here this space is important. In the case of say our hot countries, normally refrigerator space is of important. So our primary consideration is this QC. We want to have the output of QC. Whereas the cold countries like Canada and all, what they need is they want to have their inside room to be at a higher temperature. So for them, the desired output is QH. Say in the COP formula, they will write like COP equal to QH by W. So that is what is called as COP for a heat pump. And is related, I think I can show you another. நீங்க கேட்ட கொஸ்டின் பார்த்தலாமா? ஒரு நிமிஷம், 1 minute. Are you able to understand the question, Mark? Question by our Rohit.
Yes, sir.
I'll tell you what is a kind of problem. Of course, அதெல்லாம் வந்து இந்த ரெஃப்ரிஜரேஷன்ல படிப்போம்ப்பா. அது அப்ப பாத்துக்கலாம் நினைக்கிறேன். COP of refrigerator.
ஓகே சார்.
சார் அப்புறம் சொல்லுங்கப்பா.
இந்த நோட்ஸ் வந்துட்டு PDF ஃபார்ம்ல இருக்குமா சார்?
இந்த PDF வேணா அப்படியே தரேன் உங்களுக்கு.
ஏன்னா அல்ல நம்ம முன்னாடி எடுத்த கிளாஸ் தோ அப்படியே அனுப்பிச்சிருங்க சார்.
அது தரேன், பாக்குறேன். அது கொஞ்சம் வேலை இருக்கு. இந்த இதோட ரைட் அப் வேணா இல்ல, this much better இல்லையா?
ஓகே சார்.
சரி, ஓகே. people are joining. Okay, some of இப்போ என்ன பண்ணிருக்கோம், இது புரிஞ்சுலையா? அப்போ COP ஹீட் பம்ப் அதெல்லாம் வந்து வில் ஸ்டடி அகைன் இன் அவர் ரெஃப்ரிஜரேஷன் டாபிக். ஸோ லெட் அஸ் நாட் add that problem now. So there is now flow stop. I will be going beyond that. Okay, இது வரைக்கும் புரிஞ்சு இல்லையா? We could discuss so far about some 3 டாபிக் பார்த்துருக்குமா? Maximum work from a heat engine. அப்புறம் இது அடுத்த ஒரு சிமிலர் ப்ராப்ளம் we have seen, and this is about evaluating a claim based on Carnot refrigerators COP. Okay, இப்போ கொஞ்சம் we are slightly extending. Now we are going to deal with heat interaction with multiple reservoirs. So I'll read the problem. A reversible engine receives 75 kilojoule of energy from a reservoir at 750 Kelvin and does 12 kilojoule of work. The heat is rejected to two reservoirs. One is at 650 and another is at 550. Normally, our heat engine will be dealing with one heat source and one heat sink. Here we are dealing with 2 heat sink. One is at 650, another is at 550. So how much heat is rejected to sink at 650 and how much is 550? That means we are asked to find the heat rejection to 650 Kelvin. இது கொஞ்சம் slightly involved, but not to worry. We will discuss this. I will write the title now. So this is about heat interaction with multiple reservoirs. fine. We'll represent this schematically. Now the kilojoules per second, simply you can take it as kilowatt. Joules per second is what? Kilojoules per second. So kilowatt. So we'll represent the diagram. So there is a source which is available at reservoir is at 750 Kelvin. Yeah. Okay, 750. Okay, the diagram. I will represent the data later. So we have this source and there is amount of work is available and it is rejecting heat to sink. Okay, render sink heat podu. Okay, I'll represent the available data. So we have 750 Kelvin source at 750 Kelvin and sink at one at 650, another at 550. Okay, we want to find the amount of heat rejection to a source to a reservoir at 650. We want to find this. What is this? So heat taken from a reservoir at 75 kilowatt, and from that work of 12 kilowatt is obtained. So 75 kilowatt is the heat taken, and from which 12 kilowatt is converted. So the rest 75 minus 12, there is going to QC. Rest is QC, which is 63, which is shared with QC1 and QC2. So this is one equation we have. Correct, Appa? This is fine, no? So simply by energy balance. So what is energy balance?
Yes, sir.
Fine. So energy balance is QH minus W, that is equal to QC. QC is this is QH is 75 and W is 12, and that is equal to QC. QC is set between QC1 and 2. So equation 1 is available, and we need to know what is QC1. So only one equation is available. We need to write one more equation. So then only we can solve. Yeah. So one more equation, how to write? So there is a terminology available, what is called as reversible heat engine. So for a reversible heat engine, you would have come across with this term like the integral of dq by t equal to 0. Yeah. So this integral of dq by t equal to 0 for a reversible heat engine. So we need to write this. We need to write this integral in terms of what is it? QH, QC1, and QC2. So we can write this. So the source, or is the 750 Kelvin source is losing a heat of 75 kilowatt. Sorry, what is it? QH is 75. Since that system is losing its heat, so this it is minus 75. And what is the temperature of that source, which is 750? So we are writing Q by T. This integral of Q by dq by T is simply equal to QH by TH plus whatever QC1 by TC1 plus QC2 by TC2, that is equal to 0, but with proper sign. You have to use the proper sign. So I will write it again. So for QH is 75. So let us use the space available here. So 75 by 750. But 75, that source is actually Q. The Q is rejected, or is the system is losing heat by the amount 75. So minus we'll have, and this QC1 and QC2, or is so reservoir at 650 and 550 are taking the heat. So this is QC. Let us take this as 1 and 2. Okay. So QC1 by 650 and QC2 by 5. Total is equal to 0. See, always QC1 and QC2 are positive quantities. See, in what way? Because they are going to take the heat, whereas QH is a negative, which is losing the heat. So always this high temperature source is losing its energy and its entropy will decrease, and the low temperature sink that is taking the heat, its entropy will increase. So this with increase in temperature, there is increase of entropy. These things are available. That also you can verify later. You try to learn yourself, not to worry much about it. You can simply take this for granted now. So we have QH by TH plus QC1 by TC1 and plus QC2 by TC2. From this we have the additional equation. This is your second equation. So this equation 1 and 2 have to be solved together. Yeah. So we'll write this again. QC1 plus QC2 equal to 63. And here QC1 by 650 plus QC2 by 550 equal to what is it, minus 0.1 minus plus side on the bottom, and the next to the next side, which is 0.1. So these two equations you have to solve. You can cross multiply, do something, and maybe I'll take the solution directly. Maybe நீங்களே try பண்ணுங்கப்பா. Take the notebook. So you can use the equation 1 to replace QC. What is our expectation? சொல்லுங்க.
I'm getting Q sent to 650 Kelvin sink as 51.78.
Yeah, near average 52 is the correct answer, exactly. So 52 available, no? Any of you have tried this? Simply, okay, two equations are available. You do some sort of operation and get this. That is, from using 1, you can replace QC2. Here is QC2 equal to, from 1, can get QC2 equal to 63 minus QC1. And so this is your 3. And using 3 in 2, we'll be having simply 63 minus QC1 by 650. And sorry, only QC2 has to be replaced. So QC1 by 650 plus 63 minus QC1 by 550, that is equal to 0.5. Okay, you can solve this and get I am getting this QC1 as 52 and R 51.7. You are getting okay. Okay, is more than numeric. Let us discuss the problem again. So in this kind of systems with multiple reservoir, there is one equation you can simply write by the usual balance on energy. This is 75 kilowatt is the energy taken from the reservoir, and out of which 12 kilowatt is converted to work. The rest is given to the sink. So from that we are getting the equation. To get the additional equation, we are using this terminology, what is called as reversible engine. Reversible means the integral of dq by t, or this cyclic integral, is equal to 0. But in this usage, we need to check the sign conventions. So the source at QH, which is losing the heat, this system is losing the heat to the other bodies. So always, which is in terms of sign convention, that QH has to be taken as negative. So the other things are taking heat, so QC will be positive quantities. Okay, these kind of problems have come across. Normally, this kind of problem they are asking in mechanical engineering and engineering sciences, but sometimes this kind of question they can also ask in our chemical engineering as well. Still, so it's better to see this kind of problem as well. Long back, this kind of problem have appeared in our chemical engineering questions as well. Purjidapa,
Yes, sir.
Guru Prakash also. Thanks for answering. Yeah, even our other students also available. Welcome, thank you. Okay, now let us see the. So far we are seeing problems relevant to what is it, the heat engine operations. So the first two were simply based on Carnot engine, the other one based on Carnot refrigerator. Now this is also a Carnot engine working with multiple reservoirs. Okay. The reservoir is it is there is the heat sink, multiple heat sink. Okay. Now we are going to the different kind of topic, which is simply evaluating the entropy change. So air of mass 1 kg. Say in our chemical engineering problem, they used to normally give the data in terms of mole, and we will be having the value of given with a value of RS 8.314 joule per mole, in terms of joule and mole data. Whereas in mechanical and other branches, they used to give the data in terms of mass. Okay, this also appeared in mechanical engineering. But otherwise, also we should be in a position to solve any kind of problem. Say instead of R of 8.314, they are giving this as 8.314 by this 29. That's what is the 0.287. There is gas constant is given as 0.287, which is applicable for air, because R is 8.314 joule per mole, joule per mole Kelvin. So this mole you can convert in terms of mass. So for that we have this 8.314 divided by 29, which is giving this 0.287. Okay, let us read the problem again. Air of mass 1 kg initially at 300 Kelvin and 10 bar is allowed to expand isothermally till it reaches a pressure of 1 bar. Assuming air to be ideal gas with a gas constant of 0.287, the change in entropy. That is, we are asked to find the entropy change for isothermal expansion of air. So let us write this problem as delta S, or is delta S for, sorry, 1 minute. So delta S for isothermal expansion. Okay, so what is the formula for delta S? So delta S we will write like integral of dq by t, original definition of entropy change. And from this only we are going to find the final formula. So wherever possible, always try to make the derivation. But of course, it may delay you in your solution. But at least we should not worry about the final. It is better to start always from the fundamental. I insist that. So what is dq by t here? And for an isothermal process, t is a constant, so 1 by t can take it out, and it is simply integral of dq. So what is dq for this isothermal process? So always say dq. We can how to write this dq. Dq. Always from first law again we'll write. We can use this first law. First law says q delta u equal to q plus w. For isothermal process, what is delta u? Simplest question. Delta u equal to 0. Yeah, because the delta u equal to cv delta t, and for isothermal delta t equal to 0. So from which we have q plus w equal to 0. Otherwise, simply q equal to minus w. So otherwise dq equal to minus dw. So in the equation, original equation, we can replace this integral of dq with integral of dw. So delta s equal to 1 by t and integral of minus dw. So what is the formula for dw? 1 by t and integral of dw is minus pdv. So minus dw is that. So we can write like pdv. But what are all available? We are given with only pressure and temperature data. Now volume data is available. So we can write this pdv from our equation of state. So what is the equation of state? It is saying our you know this PV equal to RT. So PdV, if you take the derivative, PdV plus VdP equal to RdT. And for this isothermal process, dt equal to 0, we can write this PdV equal to minus VdP. So this is your equation 1, or yes, this is your equation 2. Here we have this 3. Using 3 and 2, we'll have delta S equal to we'll be having minus 1 by T integral of VdP. Why do we write in terms of VdP? Because we know the pressure change. Inlet pressure and outlet pressure are available. But again, still we don't know what is V. We can write this V in terms of P from P and T. Always V equal to simply RT by P. So using that, we have this RT by P into dP. So always delta S equal to simply minus R. So this is where 1 to 2. So minus R and ln of P2 by P1. Yeah, 1 to 2. So 1 to 2 minus is there. So always you can write like R ln P1 by P2. So always just to repeat. So delta S is originally defined as the integral of dq by t, and T is constant for the isothermal process. So that is taken out, and integral of dq you can write in terms of dw. And from that, from the relation of dw equal to minus pdv. So minus is there, so we have plus pdv. And since it is having in terms of change in volume, whereas we are given with only change in pressure, so better to write this dv in terms of dp, so that you can write, you make use of this ideal gas equation. So we have this we know for the process pv equal to rt is applicable, but here, okay, this t is 0, so pv you can write as pdv plus vdp. So from which we have this relation, and at last we have delta S equal to simply R ln P1 by P2. So what are all available? R is given as 0.287 and ln P1 is 10 bar and P2 is 1 bar. So R ln 10. So what is the answer you are getting? Try பண்ணி சொல்லுங்கப்பா. Let us check. Okay, we are supposed to give the answer rounded to 2 decimal places. Maybe யாராவது ஒர்க் அவுட் பண்ணி சொல்றீங்களா? 0.287 into ln of 10.
0.66, sir.
0.66. Correct. And maybe someone also ensure. And what is the answer? The answer is to be in kilojoule per kg Kelvin. Otherwise, you can also say in terms of kilojoule per Kelvin, because it is mass is 1 kg already. Are you getting part this value? Rohit, maybe, or any others? Ln 10, ln of 10. Let me also check it. Sorry, 10 or
0.66.
0.66. Okay, correct. So otherwise we will write the answer here as 0.66. Correct. Yeah, that is the correct answer only. Fine. So this problem is very straightforward only. Since we are deriving this formula, we are spending this much time. Otherwise, say the simplest formula is wherever this pressure temperature data are available, you can also get this delta S formula in a different way also. That we will see in this thermodynamic relation tab. Maybe tomorrow also I'm free. If you are comfortable, we can see that kind of discussion in the tomorrow also. How about tomorrow is possible for you?
Yes, sir.
We'll make it at the same time.
Yes, sir.
We'll do problems from thermodynamic relations. So the relevant theory also we'll discuss along with the problem itself. So we are not going to have a separate class for theory, because already we are going at a slower pace. Okay, so far 3, 4, some 4, 5 problem we have solved. We'll go further. So in the problem doubt, this problem is simpler because of isothermal. For isothermal, we have this relation dq equal to dw. So from which we have the final relation only in terms of pressure. Simple, fine. So next one we are going. slightly involved one. This is again based on our the previous problem of this integral of q by t, no? Integral of q by t equal to 0, or about entropy change for a reservoir, something like that. We'll read the problem again. So we are given with two sort of processes involving heat source and heat sink. So there is a source at I will use the other one. There is a source at 1200 Kelvin, which is losing 2500 kilojoule of heat to the sink. Otherwise, it is simply heat exchange between a source and sink. Okay, there is a source and there is a sink. From the source, amount of heat by 2000 kilojoule is going to the sink at 800 Kelvin. And there is another such system from a source at 800 Kelvin. It is 2000 kilojoule of heat is going to the sink at 500 Kelvin. Definitely, these are all irreversible kind of heat transfer, heat exchange processes. Otherwise, wherever there is a heat exchange, there is a possibility of producing work. Here, simply amount of heat is taken and it is given to the sink. We don't have any heat production. Sorry, we don't have any work extraction. Since there is no work extraction, these kind of processes are normally simply irreversible processes. Otherwise, you can simply rule out this statement. And irreversibility associated with both the processes are equal, we cannot say. And whether the process 1 is more irreversible or the process 2 is more irreversible. So how to find which process is more irreversible? Or is how to find irreversible? Or is how to validate this any of the statement? Only these two are possible, or maybe the third one also may be possible. So irreversibility and entropy change have a connection. So higher the entropy change, higher is the irreversibility. Okay, there is a applicable statement. So we can find the entropy change for these heat transfer processes. In what way it is heat transferred? So from the source at 1200 Kelvin to a sink of 800, there is a heat transfer of Q. So we know the amount of heat getting transferred. So we can evaluate the entropy change of source and entropy change of the sink, and we can get what is the total entropy change that we are going to find for both the processes, for process 1 and 2. So we'll represent the schematic. So again, the process is a heat transfer process. Heat is transferred from a high temperature to low temperature. There is a natural direction of heat transfer. The amount of heat transfer is given. We want to find the delta S for each and every process. Delta S for the first process, which is happening between 1200 and 800. The other process is between 800 and 500 with different amounts of Q transferred. So let us represent them. 1 minute, I will use still a bolder one. So this is the heat transfer process. So this is 1200 and 800 and 1200 Kelvin and 800 Kelvin and 2500 kilojoules. So how to find delta S for this? This is your process 1. Let us find this delta S1. Delta S1 is delta S of the source and delta S of the sink. For the source is losing heat by the amount 2500. So for the source, the QH is 2000 minus 2500 and T is 1200. So our source entropy of the source is getting decreased. Entropy of the sink is getting increased by what amount? This entropy of the sink it's taking a heat of 2500 and it is at a temperature of 800. So this is the entropy change for the process 1. So this is the entropy decrease for the hot reservoir, entropy increase for the cold reservoir. This is the total entropy change for the process 1. So this work out panni vainga. Maybe I can give you the correct final answer without working much. Yeah. So I'm having the answer to be equal to 1.042. Maybe check pannikonga. This is coming in. What is the unit? Which is kilojoule per kilojoule per Kelvin only, no? Because numerator is kilojoule and denominator is simply Kelvin. And the same way we can also do for the other one. We'll do that, represent the schematic, which is 800 Kelvin. It is losing to 500 Kelvin. Yeah. By what amount? 2000 kilojoule. Kilojoule, joule. Okay, kilojoule. Not worry much. So this is what process 2. So maybe you can find the Q for this process now. Sorry, for the delta is for the process 2 overall process system. So this is one is Q is 2000 minus 2000 for the source, because source is losing the heat, 2000 by 800, and the sink is getting the amount of 2000, which is available at 500. So entropy of the sink is increasing, source is decreasing. Okay, and overall entropy for the heat transfer process will be always a positive. So even this output is also a positive one. So this is found to be equal to all over the 2000 by 500. This is coming to 1.5 in my case. Correct over the 1.5 or closer to that kilojoule per Kelvin. Yeah. So you can definitely say which is highly irreversible based on the entropy amounts. Delta S. Delta S is higher for the process 2. So process 2 is more irreversible than process 1. B is the correct answer. Is it fine, Pa? Is it acceptable to you? Correct?
Yes, sir.
Fine. Thanks for the reply. Service for evaluating these kind of problems, always take up our entropy change calculations. Entropy change for calculation for the reservoir problems are quite easier, because the reservoirs are remaining at the same temperature. Say by extracting this 2500 kilo amount of energy, even after extracting, the temperature is remaining the constant. That's why this temperature we are simply keeping as constant. Otherwise, you are supposed to make this integral of dq by t, and t itself is a variable. For that process, normally a different kind of calculation is required. That kind of problem we are going to see shortly now. So is it understandable? This both the process are reversible, or is this last statement is never valid for a heat transfer process? In what way it is a heat transfer? We don't have any idea about the work. Otherwise, we can simply take this from the reservoir at 1200 to the sink at 800. This amount of heat is simply going in. So otherwise, without extracting any work, we are getting this heat transfer. The heat transfer is happening without extraction of any work. How to extract work and exchange heat transfer? Do heat transfer. So otherwise, in this, you can put a heat engine and get a amount of work, and out of this 2500, some amount can be converted into work. The balance can be transferred to the heat transfer. So otherwise, wherever there is a temperature difference available, try to convert some amount of heat into work, and the rest can be given to the reservoir, sink. By that way, if you affect the heat transfer, you'll be having a reversible heat transfer. Otherwise, this heat transfer is irreversible one, because though you have available this much of temperature difference, you are not using this temperature difference to produce any work. So whenever there is a temperature difference, we are capable of getting that, utilizing that temperature difference for running a heat engine and getting some work. So out of this 2500, if you get some amount of energy converted into work, and the balance converted into given to a the sink, then the process, it is likely to be a reversible. But again, we have to check whether this integral of dq by t is equal to 0. Then only you can say that the process is reversible. Otherwise, in what way process will be reversible? So shall we extend that? So otherwise you are QH by TH equal to QC by TC. And the Mari one. Our integral of that thing should be, so always in proportion to the temperature. The QH by TH should be also equal to QC by TC. This is the condition for your reversible cycle. Giving some connection with this problem. Okay. Or is this problem title? What is it? Checking the reversibility, or checking or finding the more reversible process. Fine. So up to this, okay. Now maybe another only one problem, I suppose. Yeah, one or two problems are available. Okay, we'll see. This one is quite easier one. You would have come across this problem, which is about quenching of solid ball with a large mass of water. This you can work out by yourself. I need not spend time on this. Instead, there is a nice, interesting problem. This is quite a nice, interesting problem. You'll spend time for at least some 10 minutes maximum. Okay, 8:10 or 8:15 will be done with. Okay, let me, of course, you can read the problem by yourself. I will explain the problem without reading it. Say we have a reservoir. What is it? It's not a reservoir actually. We have a stream of we have a hot stream and cold stream. One hot stream is available at 90 degrees Celsius. There is a cold stream available at 10 degrees Celsius. I'll use highlighter. So the hot stream at 90 degrees Celsius and cold stream at 10 degrees Celsius. Both are available at a mass flow of 1 kg per second. So otherwise, we don't have a infinite reservoir. So the previous problems were, these problems are actually a source, which means they won't, upon getting any amount of heat, that temperature won't change. Whereas the reality is not like that. We are having only finite amount of things available, at least in a chemical industry or something like that. So we are going to find how much of this work is possible from these finite quantities of streams. So we'll check the problem again. In a process industry, two different streams are available at 10 degrees Celsius and 90 degrees Celsius. Mass flow rates are 1 kg per second. And rather than wasting these resources, it is decided to connect a reversible heat engine that will continuously extract heat from the hot stream and supply part of it to the cold stream, such that the exit temperatures of both the streams are identical. Always, so one is at 90 degrees Celsius, another is at 10 degrees Celsius. We can simply mix them and send it to the sink, send to the atmosphere. But since the requirement for a heat engine is two different temperatures, we have some it's a good amount of flow. 1 kg per second means how much? 3000 kg, 3600, or 3.6 meter cube of water is leaving per what is it? 1 hour. There is a good amount. So simply, instead of wasting them to the environment or leaving to the environment, we can think of constructing a heat engine and extract some amount of energy from the hot stream and convert to work and reject the balance to the cold stream, so that both the outflow will reach at the same temperature. So the problem is the exit temperature of both the streams are identical. Slightly involved problem, but nothing to worry. I will help you how to solve this. Okay. So work of we are asked to find what is the output temperature and what is the maximum work output possible. So slightly involved. Let us start the discussion. Say for again it is a Carnot engine. Yeah, for Carnot engine, what is the total entropy change? Integral of dq by t is 0. Yeah, we know that, no? Integral of dq by t equal to 0. Cyclic integral for a Carnot. And we are going to find the say delta S of hot steam that is to make this 0, delta S of hot steam should be equal to delta S of cold. So that is one is losing entropy, another is gaining entropy. So the one will be negative and another will be positive, and the total entropy has to be equal to 0. Delta S of total equal to 0. So delta S of so how to write delta S now? Delta S you cannot simply write like dq, or okay, dq by d is correct only, but you cannot take the temperature out. Why it is not possible? Because we have only a finite stream of water, like 1 kg per second. If you take heat by some amount, definitely its temperature is going to decrease. So otherwise T is not constant, T is also a variable. So we can write this dq as CPDT, yeah, or mCPDT, because we are given with a mass flow. I'll clear this. So integral of mCPDT by T. So now R is M is actually M dot mass flow rate. So M dot Cp ln T2 by T1. So 1 to 2. So 1 to 2 is actually it is entering at TH and leaving at TF. That is this is simply does not have it as 1 and 2. It is entering at 1 minute. It is entering at TH and leaving at TF. Otherwise, the steam is entering at TH, entering at TH, and it is going to leave at TF. So there is a entropy change for this hot steam. Likewise, we can also estimate the entropy change for the cold steam. So this entropy, total entropy change will be equal to 0. That's a final thing. So this m dot Cp into ln, I'll have reduce size, ln of 1 to 2. So 2 is your TF and this is your TH. So this is your delta S for the hot. So likewise, you can also write for delta S for the cold. That is also equal to, this is again hot, m dot cold and Cp of cold and ln of that is also again changing from Tc to Tf. So final formula is going to be Tf by Tc. So this is 1 and 2. You can equate you can simply add this 1 and 2 and equate that to 0, yeah, because delta is totally equal to 0. So what is m dot of H and m dot of C are simply equal to 1, and Cp of both of the streams are the same because we have simply both are water. One is at high temperature, another is at low temperature. So otherwise we can simply m is 1 and Cp is simply 4.18. Okay. And otherwise we are simply equating delta S H plus delta S C total equal to 0. Why? Because of the Carnot engine. Otherwise we are going to construct a Carnot engine using this is it two reservoir, no, not reservoir, two streams. Reservoir means normally it's applicable for a high large quantity of large mass of steam. That is the atmosphere is the greatest sink, or the ocean is also a greatest sink, whereas our streams are not like that, no? So we have only 1 kg per second flowing. So we can write this as mCp or and CP totally this is simply equal to m dot and CPH and all you can remove because they can overall you can remove them from the left hand side. So at last you are going to have only ln of TF by TH and ln of TF by TC equal to 0. Correct, Abba? So far so good. Let me also check it because I should not confuse you. 1 minute. So 1 minute, I'm checking with the what is the problem title is 9 XC 2001. Nice problem. Actually, this was. Tension. Oh, fine. So I have the solution readily. I will also. Okay, so we are proceeding correctly. So what we are supposed to do? How to write this equation? Reduce in a reduced form. We'll continue further. So ln of a plus ln of b equal to ln a. Yeah. So ln tf by th into tf by tc. So this is the total. That is equal to 0. So ln of 0, what is it? Ln of 0 is 1. No? Otherwise, you take exponential on both sides. So exponential of 0 equal to 1. So if you take exponential on both sides, so you'll be having tf into tf, so tf square by tc equal to 1. So this is one equation available. We already we are given with th and tc, so from which you can get this tf to be equal to root of th tc. So root of tc. So what is tc? Everything to be in Kelvin. So whenever you are dealing with this kind of formula, so temperature in ratio, these formulas are with respect to absolute temperature only. So th is 273 plus 90, and tc is 273 plus 10. So it is coming to, answer is coming to 320.5 Kelvin bar. Otherwise, in terms of degree Celsius, it is 47.5 degrees Celsius. What is asked? We are asked to find the output temperature, which is 47.5. But why should we find this output temperature by this way? Why not simply by simply take this heat balance based on our formula like mcp delta T of one steam equal to mcp delta T of other steam. அது மாதிரி போட்டா என்ன வரும் ட்ரை பண்ணி பார்க்கலாமா? So we'll find. So what is the, suppose you have worked out wrongly, or since we know this heat balance like mcp of one steam, so it will be equal to mcp delta T of the other steam. How do you write mcp delta T for one steam? So we know this m dot cp and delta T is going to be 92 tf, and for this is 10 to some tf. So the you can write this mcp delta T of one steam, that is also equal to mcp delta T of the other steam. If you try that way, actually you will be getting up with a temperature of 50 degrees Celsius. Check பண்ணி பாருங்க. So otherwise there is the final temperature simply by mixing of the two streams. So whereas the temperature what we obtained is putting a heat engine or what is it, allowing this heat transfer in a reversible way. The heat transfer in a reversible way means whenever there is a temperature difference available, try to construct a heat engine between these two. Okay, so always try to construct a heat engine between these two temperature streams and get some amount of energy into, convert some amount of energy into work. And this only this QH minus QC is service. Only the QC is the heat transfer. So the from heat of QH, only QC is given to the this low temperature stream. The rest, that is QH minus QC, is converted into work. So this is a kind of a reversible process. Whereas if you don't have this W, whatever the QH is available, simply send it to the low temperature steam. You are actually wasting the energy. Otherwise, there is a possibility of QH minus QC to be converted into work. Instead, you are simply sending all the QH to the low temperature. So you are wasting some amount of energy that is equal to QH minus QC. That the maximum amount of QH minus QC is obtained from the Carnot, what is it, Carnot cycle. For a Carnot cycle, integral of dq by t equal to 0. And integral of dq by t you can write like integral of cp dt, mcp delta t for a finite stream. Otherwise, simply t is a constant, no? Whereas here t is not a constant, t itself is a variable. So you can integrate this expression and you are getting this way. So you are getting this equation for hot steam and the similar one for cold steam, and total entropy change equal to 0 for a reversible cycle. So we are getting the what is the maximum work obtainable from this cycle by constructing a fully Carnot cycle, utilizing these two temperature differences. We are seeing this final temperature of steam is 47.5. Whereas if they are allowed to mix automatically without extracting the heat, I said no, you can also find that. Maybe I will find, we'll also try to find now simply. So how to do that? Simply mcp of h into th minus tf equal to m dot cp of cold multiplied by tc, and the tc will be actually the cold steam temperature, outlet temperature will be higher, no? tf will be higher than tc. So this is the energy change for the cold steam. This is the energy change for the hot steam. So all the other things are known. So from which if you solve, you'll be getting tfs equal to 50 degrees Celsius. Okay. So if you try to do the simple mixing, the outlet will be equal to 50 degrees Celsius. So even 50 degrees Celsius is also given as an answer. So if you work out wrongly, you'll also get another answer. Okay, but that is not the correct answer. So what is the answer? The answer is 47.5. Sorry, I will use another highlighter. Okay. Okay, the problem is not yet solved. We need to find what is the work output. So to find the work output, how to do that? To get the work output, we can we need to find the heat. We can do that simply. So how to do that? Find the work. I will use another pen. Another 5 minutes maximum. Sorry, we are extending beyond, going beyond the time. So work is QH minus QC. So what is these are all, otherwise we are saying simply absolute values. What is QH? QH equal to M H into CPH into temperature. From it is changing from a temperature of TH to TF. So you can substitute this value of 1 into 4.184 into TH of 90. And for subtraction, you can simply use in terms of degrees Celsius. So 47.5 plus 273 and 90 plus 273. At last, they are going to have the same value. So you are having this 177.65. You can check yourself. Likewise, QC, you can get like M dot H and CP of H. And this is TF minus TC. Because TF minus TC is a positive quantity. So this is, sorry, a small mistake here. This is to be in M dot C and CP of cold steam. No, so this is again 1 into 4.184 into what is T7. There is TF is 47.5, and this is 10 degrees Celsius, from which you are getting as 156.75 kilowatt, and W. So W equal to QH minus QC. Fine, no? So we are getting as some 20.9 kilowatt. So there is a answer available. Let us check 20.98. Okay, we have rushed this problem. Okay, still to quickly see that this problem is a unique kind of problem. Normally, we haven't seen this kind of problem in our chemical engineering, but this is quite applicable to our chemical industry. No, so this is a case for a process industry where this kind of streams are possible. This is coming from some refrigeration unit. Say, assume this is your low temperature steam available and high temperature steam. So this is the case with hot water stream coming from a boiler unit. This is the low temperature steam coming from some refrigeration unit. These are all not needed for any of the further processes. Still, we can think of constructing a heat engine using these two temperature differences. But how to construct a heat engine, this and all we have to see sometime. Okay. Otherwise, wherever there is a temperature difference, some part can be converted into work. For that, we need to study heat in detail about heat engine. That is not possible in this kind of today's class, at least. So, what we are, how we are solving this problem? Since it is a Carnot cycle, for Carnot cycle, integral of dq by t is 0. Or cyclic integral is equal to 0, and dq we are writing as cp delta t, mcb delta t, mcb dt, and from which we have this formula, and total entropy equal to 0. This is coming from this formula. So from which we are able to get a value of tf. This tf is found to be lesser than the value if you try to simply mix the two streams. If you try to simply mix the two streams, the temperatures are coming as 50 degrees Celsius for this data. So that you can obtain this way. And QH and QC you can evaluate based on the temperature differences, from which we can get this W. Okay, with this we'll stop today's class. Maybe I will give you this kind, this PDF file. This PDF file I can share you. And additionally, this video recording will be available for you to go through this again. Oh, okay. How many of you are still available? Let us check. I will stop recording, and maybe if any of you have any doubt, I can clarify now. 1 minute. Recording is stopped.